And what is special about nitrogen vacancy center is that it is so far the only quantum system that can operate at room temperature and in atmospherical condition. Typically, quantum system needs to be isolated, well isolated. So they will be put in a vacuum, and oftentimes they will be also put in a low temperature cryostat. Nitrogen vacancy centers in diamond need none of those. So that's very user friendly, I would say. Okay, so that's two main features of nitrogen vacancy center. Okay, so that's the room temperature operation. And the other one is atmospherical condition. Okay, am I spelling this right? Atmospherical. Oh, maybe I have one O more. Okay, one. All right, so that is the most distinct feature of nitrogen vacancy centers in diamond. All right, so today we're gonna discuss how it can be used as a qubit. Qubit. How can it be used as a qubit system? Qubit is a short for quantum bit. Okay. Yep. Basically, the basic requirement for a qubit system is that it has to have a closed two-level system. It has to be a closed two-level system. That means we know that in the quantum mechanical world, particles have energy levels, right? Oftentimes they have many energy levels. Yeah. So a quantum system could have all kinds of energy levels. Now, what determines if a quantum system can be used as a quantum bit? Being a quantum system is different from being a qubit. Understand? There's a qualifier for qubit. So the condition is that you must be able to identify in your quantum system two particular levels, for example, this two, and you can excite and you can make an excitation in it. And then as you continuously drive the system, this will not go to other levels. Okay, it will not go to other levels, but you will come back to its initial state. So it needs to be almost like an isolated closed system by itself. So this is the most important criteria for a qubit, an effective two-level system embedded in a multi-level system scheme. Yep. All right. So today's lecture is mainly to help us understand how can nitrogen vacancy center be used as a qubit. Okay, and we will first start with its electronic structure, which is this multi-level energy scheme. We will explain how it comes about, and then later we will talk about how we can use the fluorescence signals from this energy levels to measure the populations in the qubit. Yep. All right. So let's first start with the diamond structure, because that's the host material of this nitrogen vacancy center. In the general sense, people also call this color center. In a more general term, color center. So if you heard color center qubit, that's basically qubits of this nature. Okay? It's also called color center. Now we'll start with diamond. Diamond has this crystalline structures of hetero structure, if you know what I mean. So have you ever seen a pyramid? Yeah? This is a tetrahedral structure, a pyramid that has the same side lengths on every side, the same length on every side. That's a tetrahedral structure. And that's what the diamond structure is. Every carbon is adjacent by, yes.
Why is it called color center? Is it
because its fluorescent light looks colorful. Yeah. So in the diamond structure, every carbon atom is adjacent by 4 carbons. I suppose this is the same in any carbon structure. It just in diamonds, they have this 3D tetrahedral structure. Okay, so chemically, they look like this, right? Every carbon is surrounded by 4. Yeah. Now, just as a side note, the angle between the bonds, the bond angles is the same for every pair. Okay, so for every pair, the bond angle is the same. Okay, so it's basically like this, and you kind of cross them like this. Yeah, it looks like this. So this is 109.5. This is 109.5, and then you try to make this also 109.5 to the other finger. Okay, so it looks like this. Yeah, like this. Okay. Okay, that's the tetrahedral structure. All right. So for diamonds, the lattice structure looks like this, or the chemical structure looks like this. Yeah. Every carbon atom is sharing how many electrons with its neighboring atom?
4?
4? Yeah, correct. Why 4? So everyone has 4. So they are sharing 4 with their neighbors. And so each bond has 2, right? Why 4?
It has 4 valence electrons, so it needs 4 for completing.
Yeah, that's correct. So carbon, the atomic number is 12. Okay, carbon 12. Sorry? Sorry again?
So you have a lot of free electrons.
Oh yeah, that is that's called nuclear defect, nuclear isotope. That is not our concern right now. When we talk about hyperfine structures or dephasing, we'll talk about carbon-13. All right, but the majority of the carbons atoms in diamonds have 12 nuclei. That means 6 proton and 6 neutron, right? Yes. Right. Carbon-13. Since someone mentioned carbon-13, it has 7 neutrons. So it is still charged neutral. Yeah. If it has 7 protons, then it will not be charged neutral. But it has 7 neutron, so it's charge neutral, okay? Okay, but these are just stuff in the material that is irrelevant for our purpose right now, for our discussion right now. Okay, so I'm gonna erase it, avoid confusion. All right, so so 6 protons implies that we have 6 electrons, right? So this also implies we have 6 electrons. So how do they distribute? So if this is the nuclei, we have electron orbitals around the nuclei, and the 6 goes like this: 2 at the innermost orbital, and 4 at the outermost orbital, right? Okay. So these are not news for you, but this little diagram will become useful for us when we talk about nitrogen. Yeah. So these are the core electrons. They kind of just like buried inside. They don't do anything. They're irrelevant. It is these 4 electrons that matters to us, and they are the valence electrons, as Mossbach said. Valence electron. Okay, so I'm gonna circle them out. Now, so in this perfect diamond structure, occasionally there will be 1 or 2 carbon atom missing. That's called defect. All right, so if we keep extending this array to a very, very large area, you know, sometimes, once in a while, you could have a little hole like this. Okay, there's nothing here. There should be a carbon atom, but there's nothing. It's just simply absence of atom. Okay, in that case, we call this a vacancy. Vacancy. And now there's really nothing there. Okay, so it's not an atom. It's not even a virtual atom. It's just empty, an empty void. But we will nevertheless use V to represent such a defect. Yep. Now, when there is this vacancy defect, what happened is the 1 electron, this carbon is supposed to share with this carbon, become a dangling bond. Okay, a dangling bond means it kind of just hangs there because it's attracted by the nucleus, so it's not gonna go very far, but it has nobody to bond with, so it's kind of just floating around. There's also attraction. This is also a nucleus, so this atom could be attracted to this or this or this, so it kind of just float around. So dangling bond, a dangling bond, a dangling bond, a dangling bond. Okay, it kind of just float around there. So there's this kind of defect, vacancy. There's another type of defect. Also only happen once in a while. It doesn't occur very, very frequently. And that's a replacement of carbon atom by nitrogen, since nitrogen is the most reached element in air. Yeah. So once in a while, a nitrogen atom could get into diamonds, or in the process of making diamonds, and they can replace a diamond, a carbon atom like this. Okay, now, so this is carbon. Now, how many electrons does a nitrogen atom have?
7.
Yeah, guys are very much prepared. Gosh. 7 neutron and 7 proton. Yeah, so that means it has 7 electrons. Okay, so how are this 7 electrons distributed? Again, we will have 2 here, okay, and we will have how many? 5. You see, the four of them are just like the carbon it replaced, but now you have 1 extra. Okay, this does not participate in bonding, so it kind of just hangs there. 1 free electrons. Okay, so this nitrogen replacing carbon atom has 4 electrons participate in bonding, but 1 that is not. Okay. Yep. Good. So these are the basic building elements of our NV center system. A carbon network, vacuum defect with dangling bands around it, nitrogen substitute with an additional electrons. All right. So this happens every day. But once in a blue moon, the nitrogen could happen to be close to a vacancy defect. That happens very rarely. Okay, even in synthetic diamonds, that happens rarely. Okay, so the integrity of diamond lattice still remains even with all this defect. Okay, so let's make a drawing. Carbon, 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 carbon. Okay. Yep. Okay. What do you mean stable? If they are adjacent to each other, I mean they are adjacent to each other by chance, not because it's a more stable configuration. You understand? There are ways, but it's not trivial. I'm trying to say is having this configuration, this is not formed because of this is the lowest energy state. This is formed simply by chance. Yeah, it's like you and your roommate, you typically don't see each other because you have different class and he has different class. But once in a while, maybe you bump into each other, you know, in the restaurant or by the lake. Yeah. Okay. So just once in a while, this happened. Now, what happened is, remember the free. So how many free electrons do we have in this system? We have this electron that was free, right? That was the additional one, and we have also this electron and this electrons and this electrons. Yeah. Do we have 4 only? How many do we have?
Should we one more for the vacancy, right?
Nitrogen. Yes, correct. Good, very good. Because see, nitrogen had 1 electron bonding with an adjacent atom. Adjacent carbon. Now, if another carbon is replaced by a vacancy, that bonding electron is also now free. Okay, so we have how many? 5. We have 5. Okay. So see, this together. Let me see if I have another color. I use all my colors. Okay, that's all right.
The box.
Maybe I'll just use this. This system forms by magic, forms a molecular structure. Yeah? Because it's not repetitive, right? If you want to have a lattice, you need to have a periodic structure. This is a standalone multi-atom system with free electrons that can facilitate bonding, even they are far away. Yeah. So anyway, this nevertheless forms a molecule. So I would think it would be more precise to call it MV molecule. Yeah. But it'll be confusing to most people if we call it that name. So most people just call it MV center. But it's really not it's really not a point. It's a group of 4 atoms, 1 N and 3 carbon, 1 nitrogen and 3 carbons, a group of 4 atoms that are some distance apart. Yeah. And the molecular structure still remain the tetrahedral 3D structure. So you have V. You have V here. N. N. C. 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 Yeah. So this is the MV molecule. And we know that usually in molecule, its atomic structure is very, very its energy structure is very, very complex. Agree? So that's why today's lecture is going to be long, because it has a complex structure. But we'll try our best to make it understandable. All right. What else? Okay, so let's start talking about its electronic property. I think cover that. Oh, one more thing to say, forgot. This is a neutral state because the electrons balance with the nucleus, right? So this is a charge neutral state. Sometimes it's called MV0, charge neutral. Yep. But that is not an MV we use in our experiment. Huh? Zero just means no charge, no extra charge, no net charge. Okay, neutral. Okay. Yeah, because there is another possibility, which is this. If there happen to be a nearby nitrogen atom that is not participate in the bonding of an NV molecule, it's just a standalone defect, like what we have here. Then remember what we said? This will have an extra electrons, right? These electrons could, not always, but it could get captured by this molecule. So here you will have not 5 but 6 free electrons that participate in the bonding. Okay. Yep.
Why would it be captured since it's charge neutral, or is it common to do it?
That's a good question. Is it a more stable state? Not necessarily. It depends on a lot of factors. So a lot of times, people, depending on their sample, a lot of times they are dealing with the charge neutral state. Other times they're dealing with MV, the charge state. In our sample, I'm not an expert in fabricating such material, but in our sample, we have MV minus, the charge state as the stable configuration for what we have. Yeah. So all right. So MV minus is what we are dealing with in our teaching lab. Okay. Right. So let's talk about its electronic structure. Now, we know that in atoms, the energy levels are discrete, right? So, but in solid, they are continuous. Why? Anybody knows? Do you know? Why in solid energy levels are continuous?
Because at higher stage, the difference in energy level became very less, so it formed as continuous.
Yes, but that does not limit. Okay, I guess you can say that, right? So when there are two quantum systems, so I'm using this to represent a quantum system. This is all the energy levels, and this is the atom. Okay, it's a square atom, and this is another atom. Yeah, and they are identical. So if they are identical, I should draw the energy level the same. Yeah, okay. When they get close to each other, their or interactions. Coulomb interactions mostly. Yeah, and when there are interactions, the energy levels will become a mixture of both. So there will be new energy level emerging, or you could call it a splitting. And this split energy level has a nature of both. So it's a combination of both, right? So if I just say that this is called S and this is called S, then this is S plus S and this is S minus S. So I'm saying that the interaction between the atoms will facilitate a hybrid energy, a new hybrid energy level that is a linear combination of both. Okay. And when you have many of this, the splitting will become bigger and bigger. Okay, so if you put 3 of them together, something like this will happen between all these 3, and the splitting will just get bigger and bigger. And as the splitting become bigger here, and there are also energy level here, right? And the splitting become bigger here. You see that the lower energy, the bottom energy level and the top energy level, they become very close to each other. So close that it's almost the frequency separation is so small that you cannot practically measure them. Yeah. So in this case, so in this sense, you can say that this there becomes a bands of energy levels. Yeah, and in each band, there are, if you look really close, all the energy levels are still discrete, but the separation is so tiny, so small that they look like continuous. Okay, so these are called bands. Yeah. Gap is this. Gap is the separation. Band is the actual energy level. Yeah. So this red thing will become a band. This black thing that become a gap. Okay. All right. So previously we talked about the carbon atom has 2 core electrons that does not participate into interactions with the other atoms, right? But the valence will. Okay, so the energy levels associated with these valence electrons, they will undergo such a hybridization process and become valence bands. Okay, valence bands. And oh, I'm sorry. It's okay. And all this will lead to a structure that looks like this. A valence band. So this is the energy level. Energies, it goes up. All the energy levels, the highest band, called the valence band, are sometimes completely filled, sometimes partially filled. But that's not the point. The point is the next band, called the continuous band, is completely empty. completely empty, no electrons there. Usually, the process goes like this. Usually, you have hybridizations of energy levels, and then you fill in electrons. Yeah, it's just like in the atom, we can have many energy levels, but there are only a finite numbers of electrons in the atom, right? So the electrons will fill from the lowest energy level up. Yeah, like this. And so you will not occupy all the energy levels. And the one that is the highest, we usually call it valence electrons, right? So it's the same thing. So when you have a band, when you have band structures in a solid, and all the electrons fills the bands. The highest one, we call it the valence band. And the one above is called the continuous band. In the typical insulator, the band gap is larger. Maybe I would say maybe larger than 2 eV. 5? That's for diamond. I'm saying for a typical insulator, okay? For a typical insulator, this could be larger, about 5, about 2. If it is smaller than 2, we usually call it, or close to 2, we usually call it semiconductor. So really depending on the band gap size, we categorize solid into different names: metal, semiconductor, insulator, according to their electrical conductivity. And that electrical conductivity has something to do with this gap between the continuous band and the valence band, because this determines how likely it is to get electrons into the continuous band. Once it gets into the continuous band, it is free to travel. Okay. So in our case, the diamond has an exceptionally large band gap. It's around 5 eV. And this very, very large band gap has some advantage to it, because when we have defect structures like this, right? Since they are not periodic, they will not be part of the band structure. So where will they appear? They will appear in the band gap. They will appear in the band gap in the form of discrete levels. In the form of discrete levels. Why? Because this is the natural, the discreteness is the natural state of energy levels. It becomes continuous simply because there are so many atoms interacting with each other, right? Since every MV centers is kind of isolated and unique, not unique, but isolated by itself, it's highly unlikely that there are an array of MV center and they can form a band structure. So they remain their atomic nature, atomic characteristic, and they have discrete energy levels living in this band gap. If the band gap is small, then this can get into this bands, and it will become not so isolated, and the interaction between the quantum system and the environment will become stronger, and that is not good for our qubit. Yeah. So one of the advantage of having this MV center hosted in diamonds, because it has a huge band gap. Okay, so that's something we want to note. Okay. something we want to note. Feynman. Okay. Now, for MV molecules, we have 6 electrons, right? MV minus, we have 6 electrons, right? All right. The molecular orbitals that it can form. Oh, by the way, so these are the hangouts for you from last time. Here. Okay. Well, I don't know if you can see it, but just like any molecular orbitals, it's just fat and irregular. It looks like this. Okay. Not much to show, but there are 4 major the energy levels that participate in the bondings are these 4, and they have special names: A1 prime, A1, EX, and EY. These are just labels for. You don't need to worry about why it is named this way. Just take it as labels for such energy levels, and that'll be sufficient. Yeah. What's important to us is how are this energy level occupied. That is what's important to us. Okay, we will have a break in 10 minutes, a 5-minute break in 10 minutes. So if I forget, please remind me. Someone, please remind me. Okay, we will have 5 electrons. How are they going to be distributed in this 4 levels? It's very important. Take a guess. Yeah.
Is it 2 in each bin because of the Fermi exclusive principle?
Mm-hmm. Yeah, exactly. So if we will take a guess how they will occupy these energy levels, what will you think? In principle, how many electrons can be in each energy level? 2. Why not 3? Marlin asked me this question last semester. Yeah, she asked why not 3?
Yeah, with a spin-off and spin-down states.
And
You
if
cannot have same quantum numbers.
If you have a third one, then you must have either spin up or spin down, right? And then that will be identical. That will make it identical to the existing electrons, and that's not allowed by Pauli exclusion principle. Yeah. Everybody follow? How many of you have heard Pauli exclusion principle? Okay, it's okay. Because they are all physics majors, so it's just natural. If you say who has heard this and that algorithm, then none of them will raise their hand. Okay, so who has heard fermion and bosons? Fermions and bosons. Okay. All right. So real quick, a quantum state. Usually we represent a quantum state as with this symbol. This is called Brod. Okay, Brod and cat. And a generic quantum state usually contains a motional part and a spin part. Okay, and these are just tags. Tag. on a quantum particle, something that this quantum particle wears. Okay, so like for example, I am wearing a blue shirt. Okay, my shoes are brown, so these are my tag. Yeah, so these are the degree of freedom in the quantum particle, and the value is, it can take discrete value or continuous value depending on the nature of that degree of freedom. But it's basically just tags on the quantum particle. So you use this tag to describe a quantum particle. Okay. Now, there are two types of, according to something called spin statistics theorem. There are two types of quantum particle. One is called fermion, the other called boson. Boson. Okay. Fermion are like lions. Lions like to stay alone. They don't want other lions to be around them. Right? They like to be alone. They want to be their own king. They want to stay away from other lions as much as possible. They don't want to be like another lion. So those are fermions. Bosons are like sheep. Sheep like to group together. They like to mimic each other. What one sheep does, the other sheep will do. When a sheep walks this way to the right, other sheep will follow. So they are like sheep. So these are like sheep. They like to be in the same quantum state as others. And fermions are like lions. They don't want to be in the same identical quantum state as others. Okay, so so electrons, for our electrons is fermions. So when they take, so this, what I draw here is motional states, because they are orbital states, right? Orbitals is how you move. You either move in this way or you move in this way. Orbitals describe your motion. So orbital is the motional degree of freedom of electrons. Okay. By the way, bosons, photons are bosons. Fermion obeys Fermi Dirac statistics, and boson obey Bose-Einstein statistics. Okay, so all the quantum particles can be split into these two categories. All right. So if you want to learn more about this, go look up spin statistics theorem. But for what we're concerned is that electrons are fermions, and they don't like to have the same tag as another electrons. So if they share the same motional state, if they have the same tag in the motional state, they must have different tag in the spin, right? And how many values can the spin state or spin tag take? For electrons, there are only two values. For other particles, it could be 3 or 4 or 5. Okay, there's really no fundamental limit to it. Okay, it just for electrons, it has 2 values. Therefore, if one is up, the other must be down. So since there are 2, we usually use up and down to name it. It's not really directional. The spin does not really have a dynamical interpretation. A lot of people use a top to describe spin. That's not very accurate. Yeah, you can just think of it as a property that takes 2 values, a binary value, 0, 1, 1 and -1, or 0 and 1. So top and down. Okay, so up and down. So that's two electrons. But we have 6. So according to Hund's rule, okay, everybody heard of Hund's rule from general physics? Okay, Hund's rules is a empirical law that dictate or that tells us how electrons will field their orbital states. Okay? Hund's rule number 1 is that they must start from the lowest. And that makes sense, right? Because because we know in nature that the lowest energy state is the most stable for some reason. Yeah, so it makes sense that if an atom wants to stack its electrons into the energy shelves, it will start from the lowest shelf and up. So Hund's rule number 1 is start with the lowest energy. Yeah, so let's do that. So each one can host 2. So we have this and this. Yeah. Now, how many do we have left? 2. Yeah. So in principle, there are 3 possibilities. In principle, there are 3 possibilities. Possibility number 1. The 2 electrons are here in the same state, EX. Possibility number 2. The 2 electrons are here. Yes? And possibility number 3.
1 in this and 1 in that.
Yes, that's correct. Perfect. Thank you. 1 here and the other here.
Can I have the opposite spins also, right?
Yes, thank you. This is
So-
the possibility number 3.
Why is it not considered 4th possibility but the same one?
Yeah, hold on. Yeah. The possibility number 3, right? But there is also another possibility that is perfectly valid. It's this. Right? So there are 4 physical possible configurations. Yeah? Now, we can tell this from this, right? Because this is a different motional state than this. This one is occupied, and now Y is not occupied. And in this case, Y is occupied, X is not occupied, right? Think of it as Y being a motional state that looks like this, and X being a motional state that looks like this. So we can easily tell this from that. Okay. Can we tell this from this? Yes. This has both orbits present. Yeah? But now, can we tell this from this?
Not easy.
We cannot, because electrons are identicals. This electron is identical to this electrons, and like there's no name, we cannot label the electrons. So this is an equivalent. They are indistinguishable. This possibility is indistinguishable to this possibility. Therefore, nature decides to have a superposition. To have a superposition. So physically, this is what the electron will do. The electrons will be in the superposition of these two configuration, and this is so this 3 is the 2 electron, 3 physically different 2 electron state, okay? And you can understand it as 3 different spin configuration in a 2 electron system. Okay, so physically it's three different spin configurations in a 2-level system. But I want you to remember them as 3 distinct 2 electron states. Okay? Now this will become the starting point of our discussion in the next half of the lecture. All right, so we will take a 5-minute break now. Take some water and use the restroom, and we'll come back at 3:40.
What makes it so you can't have both up?
Huh?
Why can't you have spin up and spin up?
Oh, that's a good question. Let me think.
Can you distinguish this by another quantum number?
That's a good question. This up is his question is, why can't you have this? I suppose you can.
But we need something to distinguish these 2 states
Very different
with the quantum numbers, right?
And
As it has the same quantum number.
Let me think.
Because they're still different energies. EY, UX are not exactly similar, right?
I would say the spin.
If it's different energy, then it can't have same spins.
Yeah.
Let me check something.
Because I looked up Hans' rule,
Mm-hmm.
and it is from Imager.
Yeah.
It says that each electron in a single occupied orbit has the same spin. They said it should be, all of them can be the same spin.
Right. Yeah.
That would be valid too then.
No, but with this structure, well, like from what I see from this structure, this has different energy states. Px, Py, Pz has different, but I don't know about Ex and Ey. It has a different quantum number, then it will be allowed. Because I don't know.
But his question is why can't you this why can't this configuration exist? And I suppose it can.
Given that Ex and Ey have different energy levels,
Yes.
we're not showing
Means
same.
like
Oh.
NLP.
Oh, sorry, I make a mistake. Okay, you're right. Actually, this is this. I make a mistake. Yeah, this is not. This is.
This cannot happen.
This could happen, but this will not be the lowest energy choice.
They would prefer to spread
Yeah,
out.
yeah, yeah. That's the Hans rule. They want to spread out.
So these would either be up, up, or
Yeah, yeah,
down,
yeah,
down.
yeah. So I
yeah.
put it in the wrong place.
Okay, yeah.
My bad, my bad.
That explains this one.
Okay. Yeah, thanks for your question.
Like you say.
Ja, jag har något sånt minne av att Ericsson gillar Roy-par från framtiden. Helt som ett mörkkursen.
De gillar ju ett par om de... Fast de gillar nog också spela ut sig för de är ändå...
I remember Hans rule number 2 is more like they should spread out. Yeah.
Yeah.
But it does not necessarily need to have the same spin direction. Does Hans rule? So for example, this versus this. Does Hans rule distinguish these two states?
Up. No.
Does Hans rule distinguish these two states?
I think so. Due to this picture.
But why not this?
We should all be in the same direction. But that is given that this is the same.
The same.
Subshell 2p. But this would also be the same. Maybe it wouldn't.
I don't know. So it looks like Hans rule prefers this spin configuration over this. Is there a reason for it? I know, but why? It has a what? Send energy. This has two. This two has the same energy. It has the same energy as which?
I remember if their spin down and spin up is not the same, the energy is not the lowest.
So this is the lowest.
Yeah.
Not this. Why? Anybody know why?
I think the Wikipedia is say the angular momentum depends on the angular momentum. So the lowest energy is the maximum angular momentum.
The lowest energy is the maximum angular momentum.
So I think in the upper one, angular momentum is larger than the lower one.
Okay.
But then how is the third configuration? Okay.
Oh.
Yeah, interesting. I know that.
Then if you cannot have alternative unit same, but these states we have alternatives.
Yeah. That's right. So it violates Hans rules, it appears.
And Hans rule is just to fill the lowest energy. It's not for the
Yeah, it's
excitation
a
or
ground state
anything.
configuration. But this is also ground state configuration. Yeah.
Oh.
So why the largest angular momentum?
But I think the angular momentum, what I say, is the orbital momentum.
Yeah.
That's also.
But still.
So maybe these two they are kind of same. I'm not sure. Because the first row is
Spin orbit coupling.
Maximally spin.
Oh, maybe spin orbit. Well, maybe because spin orbit coupling. Because these are p, right? These are 2p, and And if you have spin-orbit coupling, then this these two will have different configuration. So if you take into account LS coupling, maybe that's the reason. Yeah. Okay. So we have a puzzle now. Yes. So according to Hans rule number 2, this spin configuration has a lower energy than this one. So in the ground state, atoms will take this configuration. Now the question is why? Hans rule number 2. Because I got this question too last semester. Actually, from RTA, from Han, and we didn't get to discuss this. But yeah, this is
Lord Coulomb direction.
Yeah, I thought something that talks about how to minimize the Coulomb energy, and they can stay a large distance apart on average if they are in opposite.
so for large L value, some of the regions have same direction. Large L value, large system. Every sense they could consistently be the opposite side. They could be on the opposite side. But it still doesn't explain why the spin
Okay.
direction. How
I
the
think
spin
the
direction.
basic thing about this case and the Hans rule is defined for atoms. So in molecules, in the degeneracy, there is some other differences. So when I check for Hans rule in molecules, it says field degeneracy pi and pi star at once.
But this is parallel spin.
Parallel spin, okay.
Yeah. Yeah, this is the same as what he was showing me. So the for low L value something.
So this is like the physical explanation to why we get higher energy.
I understand this argument, but if I have large L, right? So they are like far from the nucleus. This is far from the nucleus. Yes, they could be. They could have the same spin direction, but if they have the opposite spin direction, that's okay too. I don't see any reason why this is worse than this, unless you introduce the spin-orbit coupling.
Mm-hmm.
You know what I'm saying?
Yeah.
Right? Because if you don't have spin-orbit coupling, then the spin is just irrelevant. The spin orientation is just irrelevant. It's like a phone they carry and never dial or never turn on. Okay, well. James, are you better? Are you okay? Do you think you can manage to do the experiment? Okay, great. That will be your partner. Yeah, what's your English name?
Indy.
No, English name. not English translation of your Chinese name, but English name, like real English name.
I don't have English.
Well, can you make up one? I know.
I don't know.
Everybody makes up their, well, I don't know. Everybody give their English name so I can remember you easily. So we have Phoenix, Lily, James, Simon, Vita, David, Mosfa, Andy, Tom.
Just call me Ling.
Lin,
Yeah,
okay. Lin, Lin. All right, I'll remember you by that. Lin. Border this. Lin, okay. All right, so Lin and James, YouTube will be in the same group, and the group name is Bob. So we have Alice, Bob, Charles, Charlie, and Eve. Okay. So I guess we don't need to go to plan B. All right, cool. So let's resume. Where is my note? Oh, here.
It said it's an excited state.
Violet.
Okay, thanks. All right, so there are two things I want to note from our previous discussion. Number one, I drew this wrong. These are not these are here. Okay? And these are here. So there are two different orbital states. All of them are in two different orbital states. And this is in agreement with Hund's rule, because Hund's rule states that you want to have the electrons spread out as much as possible. If they are, so this is definitely, this configuration is definitely, I mean, yes, this is possible too, physically possible, but this definitely has higher energy than this one, right? Because these two electrons share the same orbital, they just have different spin direction. And if they share the same orbitals, then once in a while they can get really close to each other. Yep. So this, but this in this scenario they share two different orbitals. They have different orbitals, and for the most part the orbitals are orthogonal to each other, so they will not the overlap between their wave function is minimized. Okay, so you want the electron spread out as much as possible. Okay, so for the sake of ground state configuration, for the purpose of figuring out the ground state configuration, we want to spread out the electrons as much as possible. So previously the four scenarios are this four. Okay, all of them are in different orbitals. It's just that the spin orientation, these are the same up, this is the same down, and this is up and down. Okay, and like I said, these two are physically indistinguishable, so nature dictates that the electrons will take a superposition. Okay, everybody familiar with the concept of superposition? This is not superposition from linear. Well, have you heard of superposition? Yes or no? No. Okay, good. Great. All right. So I'll take 1 minute to explain what a superposition is. All right. So I'm gonna ask Tom come up, and I'm gonna have a chair, two chairs actually. Can I borrow your chair? Yeah. It's okay. Leave your jacket here. Leave your jacket. Actually, I want your jacket. I need your jacket. Thanks. So I have a chair with jacket and a chair without jacket. Okay? So these are two distinguishable chair. Yes. Tom, as a classical particle, can only take one chair at a time. So please have a seat. So he can either sit at the chair with no coat, or the chair, please move to this chair, or the chair with coat. But what Tom cannot do is to sit at the two chairs simultaneously. Yes? So that's a limitation of classical particle. Thank you, Tom. But quantum particle can sit at two chairs at the same time. Okay? Being two distinguishable places at the same time. So that's called a superposition. So these two are physically, energetically distinguishable, but nevertheless, they are still different in a sense. So the electron can be in the superposition of these two states. Superposition means take two states at the same time. Right, thank you. Okay. Okay. And there was another discussion on, so Hund's rule number 2. I remember spread out. Okay, starting with the lowest energy is number 1. Number 2 is spread out. And there was a discussion during the break whether this should be the lowest energy state, or this should be the lowest energy state. Okay? According to Hund's rule, I don't know if this is the second or the third. Second, so it's part of the second. So Hund's rule says it should spread out and plus same spin direction. Same spin direction. Yeah? But soon you will see that in our case, this configuration actually has the lowest energy state. So that appears to be a violation of Hund's rule. Yeah? So there was a discussion during a break why that is the case. And I don't have a good answer to it, but I suspect that the reason in Hund's rule that this should be in the same spin direction is because the spins are interacting with its orbital, with the magnetic field from its orbital states. So this is called the spin-orbit coupling. When electrons is circulating around the nucleus, this is an effective, it sets up an effective current. And that current will generate a magnetic field. And that magnetic field will, in turn, interact with the spin of the electron itself. Okay? So all these orbitals that each electron take will interact with the spin. And maybe the combined effect, which I don't know for sure, but maybe the combined effect is that if all the electrons have the same, and in addition to the LS coupling, you also have spin-spin coupling from the same principle. So because each spin also can generate a magnetic field, and that magnetic field can also influence other electrons. So in the multi-electron system, things like this can become very complex and convoluted. Okay, but anyway, Hund's rule number 2 says that it should spread out as much as possible, not taking the electron not taking the should avoid to take the same orbital state. That's that's easy to understand. But it also says that the spin should be parallel. The spin should have the same direction. And I suspect the reason behind that is LS coupling, spin-orbit coupling. In this case, however, it's not saying that we don't have LS coupling, but the effect of SS coupling could be larger, and that could be the reason why we have a case violating the Hund's rule. Okay, now I'll start to get into this. Okay, so that's number 5. So we have 3 states. This, and this. 1, 2, 3. I will put a notation like this to denote the state. So up, up. So the first place simplified EX, and the second place symbolized denotes EY. And for this, we have up, down, and down, up. Yep. These 3 states are energetically equivalent. Yeah. These 3 states are energetically equivalent. The they are energetically equivalent. Okay, let me just number them: 1, 2, and 3. So they are at the same. So if this is energy, they have the same energy. Okay, they're energetically equivalent because the energy according to the orbital are the same, right? Each orbital has 1 electrons, and that's the same case for all the states. So they are energetically equivalent. However, if we take into account of this spin effect, then this degeneracy means the same. This degeneracy will be split. Now the question is, who is lower and who is higher? Okay. Turns out oh, by the way, a degenerate system, a degenerate state that has 3 states, 3 components, called triplet. If it has 2 components, called doublet. Okay. So we often call this 2 electron state a triplet, a 2 electron state triplet, and the triplet has 3 components. Triplet, and the triplet has 3 components. We use M to distinguish them. So M equal to -1, 0, and +1. Okay. Right now, there's no physical meaning to this M. It's just a label. -1, 0, and 1. That's just a label. You can call it ABC. A triplet has 3 components, 3 parts. So this triplet, this is what we call m equal to 0, and this is m equal to -1, and this is m equal to +1. Okay, so the triplet has m equal to ±1 higher if we take into the spin-spin interaction.
0, right?
Oh, sorry.
From 3.
Sorry. Yes, you're right. So this is 0. So this is spin interaction. Okay. So what is a spin-spin interaction? Does everybody know what a magnetic moment is? Yes? How about you? No? That's fine. So when we have a magnet, this is out. Bye-bye. So when we have a magnet, we have two poles, right? N and S. And the field goes like this. The direction goes out from N and comes back to S. Yeah? Now, when we put another magnet close to it, what will happen is it will orient itself so that the N is matched with S here and S matched with N here. Correct? We've heard this, right? Now, from the macroscopic view, from a microscopic view, this magnet is just a macroscopic collection of tiny magnets. So at the atomic level, each atom in the magnet carry a tiny thing. It's like a tiny magnet. It's like an atomic magnet, and it's called magnetic moment. Yeah, and that magnetic moment generate the field just like this. The direction, the point, it points. It has the same orientation as the magnet. Okay. Now, so you could say that the field here, the field here has the same direction as the magnet, as the tiny magnet, but the field here has the opposite direction as the magnet. Okay. So let me just point that out. So B here has the same. Sorry, it has the opposite direction as the magnet. Okay. Now, the reason why the magnet orient itself like this is because the magnetic energy is a dot product. Do you know what dot product is? So dot product is just a multiplication between two vectors. Okay, so it's a dot product between the magnetic moment and its local B field. Now the local B field here is opposite to the magnetic moment. Let me just call it 1. Okay, so let me call it this B1, B1. Now if you have a magnet that comes here and another tiny magnet that has the same orientation, let's call it mu2, then that its energy is going to be minus mu2 dot B1. Yes? Now, since B1 has the opposite direction from mu1, this becomes this. You see? So this becomes the dot product. The magnetic energy between these two magnetic dipoles is the product of its magnetic moments. Yeah? Therefore, if they have the same direction, that's a high energy state. Just from the math, right? If they have the same direction, that's a high energy state. If they have the opposite direction, you have a negative value, and that's a lower energy state. Yeah? So from the microscopic point of view, an opposite orientation, a magnetic moment orientation, will give you a lower energy state. And if this applies to every atom pairs between the two magnets, the entire magnet will follow the same rule. And that's why this flips. Because this is the direction from S to N. That's the direction of the moment. This is the direction of the moment. Okay? Now, for spin, it's the same story. Sorry. This is what spin is. So the moment we just talked about actually originate. This moment that we just talked about, this tiny atomic magnetic moment originate from the electron spin. How so? The relation is such. It's called G E to M and S. Okay. So this is the spin angular momentum. Okay, and this is just the electron charge, electron mass. G is something you don't need to worry about. Something that is close to 2, but not exactly 2 because of vacuum field interactions. Okay, so but this is close to 2. All right, so I just want to say that the magnetic for electrons, its orbital momentum L and its orbital angular momentum and its spin angular momentum both can generate a magnetic moment, and that magnetic moment can generate fields. Okay, so if you have a spin, so you can see this as an equivalent of spin, except that for spin, the direction is the opposite. Spin 1, and this is spin 2. Yeah, but the math here pretty much stay the same. Spin 1, because we have minus sign here, minus sign here. So the energy is proportional also to the direct dot product of the two spins. If the two spins are oriented in the same direction, that is a higher energy state than this. Okay. Therefore, it is understandable why n equal to 0. We call this n equal to 0. It's just an n. It's just a label. Why n equal to 0 has a lower energy state, because they have the opposite spin direction. Because the spin direction are opposite to each other. But here they are the same. this gap, the energy of this gap is often characterized by a frequency. Because for photons, energy is equal to the Planck constant times a frequency, the oscillation frequency of the electromagnetic field. So often we will we use this convention, and we will use frequency to denote energy gaps. In this case, we have the energy gap is 2.875 gigahertz. Okay, this is in the microwave regime. If you use laser trying to excite this transition, it won't work because laser has the frequency at a terahertz range. Okay, and this is gigahertz. Gigahertz is 10 to the 9, and terahertz is 10 to the 12. So there's like a huge 3 orders of magnitude difference. So here we use microwave for energy state manipulation. Yeah. Okay. Now that is so we're done with electronic structures. That's pretty much what I want to say about electronic structures. This is the end of the deal. Okay. It has. Okay. Cool. That's the ground state triplet, and the ground state triplet, due to the spin-spin interaction, split into two groups, and one has, I guess you can call this doublet, but anyway, one has 2 components, and the other has only 1 component. Okay. Now, what should we do? Oh. Let's come back to this. The overall the complete molecular electronic structure looks like this. Okay. This is the complete molecular structure. Everything we just talked about, this is the ground state triplet. Okay. This is an excited state triplet because it has a higher energy. It also have so 3 here means triplet. So this has also, so this has m equal to 0 and equal to plus minus 1. This is m equal to 0 and equal to plus minus 1. Okay. This is a singlet. This is a singlet. They have so this is the energy gap between these two states, this is microwave. But between these two, this is 633 nanometer, so like terahertz. And there are, in between, there are also another two. Okay? And I think this is about 1.9 gigahertz. I don't know. They are just molecular orbital names. There are symmetries associated with different molecular orbitals, and all these numbers are, there's like a naming system for it, which I'm not familiar with. So and for us, since we're not chemists, and unless you're like doing research on molecular structures, this is really not important. Just take you can call this David and this Tom and this Lily and this Phoenix. It wouldn't matter. Okay, they just come up with a universal naming system so that it can apply to all different kinds of molecules. Since we're only studying MV center molecule, we don't need to worry about that. Okay. Now, give me a second. Oh yeah, sorry. Now 1.9, it is 1.19, so about 1.2 gigahertz. Okay, and this is 1.4 gigahertz. Yeah. All right, so I just want to let you know that they are also, so we've spent a lot of time talking about this molecular state and how they are, how the atoms, how the electrons occupy different states, right? These two have the same. So for this one, we have here, right? And it is just how different, how the spin of, so in terms of population, n minus 1, plus minus 1, and 0 all have this configuration, right? They have one electron in each orbital. But for here, it is slightly different. It has 2 in the highest level. So that's why this has a higher energy state than this. But concerning, so here we have different spin orientations. Here you also have different spin orientation between these two, right? So it also has a triplet. Okay, and this is just a singlet and the 2 electrons. The energy levels here is different from what we have there, but what I want to say is that the singlet is different from the n equal to 0 triplet by the sign. So here we have plus, I believe. But if the superposition has a relative phase of 180 degree, then that's a singlet. Okay. So this both are the spin for both are singlet, but the molecular orbital states are different. Anyway, this is the complete molecular electronic structures of MV center. And this schematic is very helpful for us to understand the fluorescence property, the behavior, and also the optical pumping of the quantum system. Okay. So, like I said, when you have all the blue are dead. Oh, I have green. Yay. In our sample, we have how many MV centers? 1, 2, 3. How many do we have? Huh? Yeah, probably millions or even trillions. Who knows? Depending on your concentration. But the point is, each one of them, if I use an arrow to represent each MV center, since this N and V, it has a certain orientation, right? If I use arrows to represent each MV center, this is not a spin. This is just a representation of the MV axis. Okay? Let me call this MV1, MV2, MV3. Okay. At room temperature, all of them are going to be in this state. Okay? All of them are going to be in this state. However, this is a triplet, right? So it actually has two distinct energy states. Here we have two degenerate components, two degenerate states. So basically, 1, 2, and 3. Yeah? Okay. Now, MV1 could be here. Yes? If that's the case, then it is in the truly lowest energy state. MV1. But MV2 could be here. Why? Yes, naturally you will prefer to stay here, include 0. But due to thermal excitation of its environment, the crystal has temperature, right? Has the same temperature as the ambient temperature, so like 25 degrees C. So that little thermal energy is enough to overcome this energy gap, 2.875 gigahertz. So that little infrared energy, or far infrared energy, not infrared, microwave energy, is enough to excite it to here. Yeah, none of them will be here or here or here. All of them will be distributed between these two states. Okay, so MV3 could be here. MV4 could be here. MV5 could be here. Yes, so all of them are in different states. All of them are in the ground state triplet, but the actual physical state, they could occupy different physical states. So 4 and V5. So NV, so this is 0. Let me just denote it. This is +1, 3 is -1, and 4 is +1, and 5 is 0. So that's what it looks like in the thermal distribution. The first thing we want to do when we manipulate a quantum system is to prepare every member of our ensemble. Ensemble means a collection, okay? Because our signals, we're taking signals from this ensemble. We are not able, like, for what we do now in the teaching lab, we are not able to resolve into individual MV center. It is possible, but for our apparatus, we don't have the ability. So we're taking signals from the ensemble. And in that case, it will be necessary for all the members of the ensemble, to have the same state in order to give a distinguishable signal. Yep. Let me just give you an example. 1 and 3. 1 and 3. If you apply a microwave excitation and you excite MV1 to the excited state, okay? Suppose you can measure that signal. There is a signal that tells you it is in the excited state. Maybe the signal is a voltage signal and you get a plus 0.1 volt increase in your signal. And that shows MV1 is in the excited state, right? Then the same pulse, the same microwave pulse could also make MV3 go down to the ground state. In that case, your signal will have a minus 0.1 volt difference due to from MV3's transition. Yeah. Since the signal we collect is an ensemble average, all of this will need to be summed up, and it will give a net difference of 0. In other words, we will not be able to see the effect of our microwave because this boosts our signal up, the other boosts it down. They cancel each other. So preferably, we want to prepare everything in the same state. In the same state. It could be this one, or it could be this one. The lowest energy state, the ground state, is certainly the natural choice, right? So that's why a lot of quantum systems are hosted in a cryogenic structure. Now, cryogenic structure provide cooling ability to reverse the thermal distribution. So the thermal distribution looks like this, right? So the cooling, so this is the state number. So you have like many states and they are all occupied differently according to the Maxwell distribution. But the cooling mechanism, whatever you use, maybe through contact cooling or through laser cooling, is supposed to prepare the system in a very narrow distribution at the neighborhood of a single state. Yeah, that's the prerequisite of quantum gate operation. Otherwise, you will not be able to get any distinguishable signals from your operation. So this is called cooling. So in one of the magical features of MV center is that it has this ability to be cooled by laser. Yeah, it has this ability to be cooled by laser, but this type of laser cooling is different from the laser cooling that we talk about when we deal with atoms or molecules. Those are not motional state cooling. These are electronic state cooling. Okay. Okay. Now, let me explain how. And this laser cooling is in general this laser cooling technique that we use in here. This laser cooling for the electronic structure. In physics, we call it optical pumping. And I want to just quickly explain how this works. So when you shine a laser, so in a so I told you that this separation is 637 nanometer, right? So if you provide a laser energy that is higher than this, then in principle you can get this up to here. Wow. Okay, sorry. So in principle, you need to use exactly the same wavelength to match the gap. But in the experiment, we are not using 637. We're using 532 nanometer. Why is that? So that is a higher energy. That is a higher energy than what is required here, right? And it shouldn't work. Why do we use that? Anybody has any idea?
Goes up to the M+1 state, and the M0 to directly to M+1.
No.
Of the top state.
That is not allowed because we are using linearly polarized light. Yeah.
Is it like lattice vibrations or phonon?
Yeah.
Phonons that take its extra energy.
Yes, you're right, actually. So the reason we're using a different energy, that has some strategic reasons. Remember, we said that the MV center is embedded in a carbon diamond lattice. Yes? And diamonds are very rigid. The bonds are very rigid, right? So the vibrational conductivity is very, very good here. And also, oh no, sorry, that's not what I want to talk about. Remember that the picture that we drew, there was N and a void, and C and C and C, right? Since there's a lot of space here, this MV axis can vibrate. The length, the distance between N and this center can vary. So you can see this as like a nuclear oscillation. Although we don't have any nuclear here, but N can oscillate along this axis. Okay, and it can do so very easily because, I mean, it's supposed to be a very rigid structure, but now we're missing one atom, so the structural integrity is partially compromised, and so now this oscillation, this mechanical oscillation, can be easily introduced to the MV molecule. Okay, so just like any molecule that vibrates along its bonds, so will the MV center. Now, when you have wavelength, when you have an oscillating structure and you shine light to it, then because of the Doppler effect, the frequency that you sent will appear to have a different frequency, and it can absorb it. So if you send a 532 nanometer, right? Although this energy is higher than this energy gap, 637 nanometer, but because it's vibrating, so you will be able to. So this, due to the Doppler shift, it will appear to have a lower energy than it actually has, so it can be absorbed. Once it gets absorbed, the energy will get distributed into two parts. One is the phonon. One is the vibration degree of freedom, and the other is the electronic degree of freedom. Okay. So, so this is 637 nanometer. So in principle, all the excessive energy that we see here those goes to the phonon. Okay, so the absorption so the absorption in principle should go like this. It will extend to a shorter wavelength regime. Okay. Now because earlier I mentioned that diamonds are very rigid, has a very rigid structure. So any vibration you generate on the MV centers can propagate out to the lattice at a very, very short time, maybe femtosecond. So if you apply a green laser and excite to this phononic sideband, okay, then this vibration will convert to propagating phonons and propagate out. And so in that case, your vibration will stop because you propagate your vibration energy out through phonons. So your vibration will go down in the vibrational levels, okay, and you come back to this state, okay. So and then what happened next is that you will release this energy by radiation again. You release this energy by radiation again. And just like when you excite, the excitation must obey the so-called optical selection rules. That means if you're using a linear polarized laser, then you will not be able to, you should conserve this M number, okay? Okay, I won't go much into the detail of it, but this M actually has a physical significance, and it has to do with angular momentum. So if you're using linear polarized light, because there's no net angular momentum carried by the light, so you cannot introduce any angular momentum change in the system. So if you start with n equal to 0, it must go to n equal to 0. Okay, and if you start with n equal to plus minus 1, you must go to n equal to plus minus 1. Okay. Now, the decay also obey the same selection rule. So you should go down to n equal to 0, right? But instead of going down directly to n equal to 0, it could also, so this vibrational level really is a further splitting of that electronic level we talk about. So so it's like this equal to motion, electronic motion, and this is spin, right? So that vibration is basically adding another tag to the quantum state. It's called a mechanical vibration, okay? And this will make this further split into many very, very thin levels, okay? Each of them will get split into a cluster of closely spaced vibrational energy levels. But what I'm trying to say is, when you decay, instead of decay to the lowest, absolutely lowest ground state, you can decay to one of the vibrational states. And that also will cost so this will cause the MV center to vibrate, and that after a brief moment, that vibration will get converted into phonon and propagate away into the Corbin lattice. Okay. So this decay process, this is not radiative. Okay. This two here, this phonon sideband, this is called phonon sideband, because this is at the site of what is supposed to be, what is supposed to occur. This is at the site. This phonon sideband, so we have a excitation sideband, which is this, and we also will have an emission sideband. Okay. For the same reason, so I can decay. When I decay, I can decay to an energy state that is slightly higher than this, and then the excessive energy can decay out through phonon propagation, through generation of phonons. Okay? So it looks like this. All right. Say again.
Vibration state.
What about it? Vibration? Yeah. Because, like I said, so this MV center that we talk about, right? Previously, we focused on the electrons. But there's also the nuclear motion. Okay? So that degree of freedom we didn't consider earlier. But if we consider then that's a further splitting of the electronic energy levels.
So we can control the nuclear position in experiment.
Control is a big word, but yes, we excite it. Yeah, and actually this naturally occurred.
Is there any use or any factor we can use in quantum sensing or this topic?
I don't know. Maybe. I would imagine that perhaps somebody has the same idea as you, and they're trying to control the nuclear motion of the NV centers. Yeah, but for our discussion here, it is just a process that occurred. We don't control in an uncontrolled manner. Okay. So we have, like I said, the excitation sideband, phonon sideband. Okay, so that's this. And we also have the emission phonon sideband. Okay, and the difference between this electronic gap frequency and the sideband, this is the phonon energy. Okay, this is the phonon energy. Now, the decay radiates energy, and that energy radiates is called fluorescence. This effect, this phenomenon is called fluorescence. So this is the fluorescence spectrum, and this is the excitation spectrum. Typically, excitation and emission happens at the same energy, right? If you have this much energy gap, then you need to use this much energy to excite it. And when you decay radiatively, then you will emit the same amount of energy. So normally they are at the same frequency. And normally, if this is the case, you will not be able to detect its you will not be able to detect its quantum states, because your pump wavelength is the same as your signal wavelength, right? Now, thanks to the phonon sideband that we have here, the excitation spectrum is separate from the emission the emission spectrum. Furthermore, because the efficiency, because of the efficiency in this transition, so from one vibrational level to another vibrational level, there is coupling efficiency. And the coupling efficiency, so if the vibrational level is marked, okay, so just in general, a mechanical vibration can be seen as a harmonic oscillator, right? And a harmonic oscillator has many motional states, and we can number them as, for example, k equal to 0, k to 1, k to 2, k equal to 3. And on the effective, this is the effective coordinate, q. Okay. On the wave probability distribution on the effective q has this shape. Okay, if you find this very strange, that's okay. What I'm trying to say is that when you go from a vibrational level here to a vibrational level here, the transition between vibrational levels will depend on the overlap of the wave functions. Okay, And this is called a Frank Condon. Frank Condon. I don't know how to pronounce it. Condon principle. The overlap between this initial, let me just call initial, and this is final. The overlap between initial and final wave function determined the transition probability. Okay, so after calculation, it turns out that 0 to 2 give the highest overlap, largest overlap for MV centers. Therefore, this does not peak at 637. This peaks at 532. Okay. Yeah, and this peaks at about 700 nanometer. That's infrared, near infrared. So this is pretty awesome because you see the spectral separation between this is about almost 200 nanometer. So the problem that we had was solved because thanks to this, right? Thanks to the Frank Condon example principle. Now we can use a 532 nanometer light laser to excite this energy, and then the fluorescence light we can detect in another channel, and we can use specialized optical component to separate these two wavelengths. So that enable us to tell through optical means the population distributions in the quantum system. Yeah. Why? It's like I said, the efficiency of the coupling determine the strength of your the strength of your signal in the fluorescence in the emission spectrums. Yeah, and just so happened that 0 and 2 couple the strongest for MV center. That's why it peaks here.
If I want to understand, I need to do what?
Give me a second. So you can see this is if you want to understand, then you need to read papers.
Many papers just show this result.
Yeah, but the basic mechanism is this. Do you understand this? Do you understand why there is a peak? Okay, let me explain again. It should look like what we normally expect is this, right? But why is there a peak here? Well, because when you go from, say, an energy level, sorry, let me just call it K equal to 0. K equal to 0, right? You decay down to which K? Which K is the most efficient channel? 1, 0, 1, 2, 3, 4. Are they all equivalent? No, they are not equivalent because their wave function look different. So depending on the overlap of the wave function, the transition amplitude, the transition probability depends on the overlap, the wave function overlap. The more the wave function overlap, the higher the transition probability. So it just so happened that for MV center, for this particular system, that K0 and K equal to 2 couple the strongest. Okay? So when you go from here to here, it is 0 to 2. When you go from here to there, it's 0 to 2.
From K to K equal to 0 to K equal to 2, and the wavelength is 700.
Yeah.
Okay, and why we how we find 532 to
That is also just the same thing. It's reversible. So if 0 and 2 couple the strongest, then 0 here, 2 there also couple the strongest. Okay, so maybe I should change this to 2 to 0. Sorry, this is 0 to 2, and this is 2 to 0. No, this is also 0 to 2. Anyway, the point is, these two wave function couple, they overlap the most. Okay. In the
in the excited stage, from it will be in K to 2 and it will go to K equal to 0 through phonon excitation, then de-excite to K equal to 2, then also phonon excitation go to 0.
Right. Yeah, that's how it works. This cascade is really fast. Okay, so you go from 0 to K equal to 2. That's the strongest. And then you go down, you immediately go down to K equal to 0, because that phonon, the decay through phonon channels, phonon emission is really fast due to diamond structure. And then from here, 0 again to 2. Okay, but this is K equal to 0. The excited, so the electronic state tag is E3, and here the electronic state tag is A32. You got it? You get it? So it looks like this. Yep.
When we use some technique to fix the nitrogen atom,
Mm-hmm.
then this it will become just a single peak because no vibration state.
Yeah, if you can prevent it from moving, yes.
I just want to understand.
Yeah. Yeah, in principle, these are all single peaks. It's just that there are so many of them. All different frequencies. A lot of different frequencies are possible.
Nitrogen atom oscillates really fast, then maybe these two peaks will separate. We don't know. Need to calculate, right?
Yeah, maybe. I'm not saying that's impossible. Maybe. Okay, I have not done that calculation. I just know this is how it works. Okay, so the point is that the excitation and the fluorescence are far separated, and that enables us to detect the quantum states through optical means. This technique is called ODMR, optically detected magnetic resonance. Okay, you will see that in your menu, ODMR. Okay. All right, so coming back to this. So all this is just to explain why we're not using 633 nanometer to excite the system. We use 532 instead. Okay. Now I want to talk about optical pumping, which is how we initialize the ensemble to its lowest quantum state. Now, when you have, this is 7. Okay.
So when it de-excites from k equal to 0 to k equal to 2,
Mhm.
whether it will be 532 or 700. It's also 532.
700.
700.
Yeah. Okay. Okay. Okay, this is the last part. So let me not draw those fine energy structures. I'm just gonna draw the gross structure. Again, this is A32, E3, A1, E1. Okay. So in the experiment, we initialized the ensemble to its lowest ground state by shining 532 nanometer laser to it, which will make it go here, right? Okay, and suppose this is n equal to 0, then this will be also n equal to 0. Yeah? Now, when it decays, when energy decays out, it's primarily radiative. So for n equal to 0, optical excitation up, optical de-excitation down. But for n equal to plus minus 1, the story is a little different. When this gets here, two things could happen. It could decay through both radioactive channel and non-radioactive channel. The radioactive channel is of course, we'll bring it back to n equal to plus minus 1. But the non-radiative channel will go to this state. You mean the branch ratio? There are some numbers in the menu, in the contact menu. I don't have it by heart. This is the primary. This is the primary channel. This is the secondary channel. Okay. What I know is this is strongest. This dominates, and this is less important. However, this exists, and thanks to this, because when this cascade down, so from this state to this state, there are also radioactive channel and non-radioactive channels. It doesn't matter to us, but just so that you know that going down, boom, 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 there are ways for it to go down. And then from this point, there are two paths. One goes to the n equal to 0, and the other returns to n equal to plus minus 1. Now, this path number 1, that conserve populations in the n equal to plus minus, right? Because how much you bring up, you return the same amount. Yeah. But this channel, this secondary channel, leaks population out from the n plus minus subsystem. So after one cycle, so say you have 100. Say if you have 100 MV, right? And the first MV undergo this. Say you have 100 MV at the thermal distribution, you have 100 MV here. So 100. Okay? And you have also 100 at the, okay? So say they're about the same at the thermal equilibrium. Now, this 100, after shining the same green light will work on this, the first 100 and the second 100. Though the same green light will work on both of them, both groups, right? All of this will be carried to the excited state here, and then come back, and then they will return to its original state. All of this will be carried to this excited state. The majority will come back, like 80, maybe say 80 of them will come back, and 20 will go this way. And maybe in this process, 5 out of 20 will go this way. So let me just say 5, 15, okay? So this is 20 going this way, and then 18 returning back. So in one cycle, you lose 5 MV to the ground state. In the next cycle, you also lose, so if this is 5%, in the next cycle, you also lose 5%. In the next cycle, you also lose 5%. This is called optical pumping. After you pump it for many, many, many cycles, all the MV will get collected to the n equal to 0 state. That's how you prepare the MV quantum ensemble to the ground state. Okay? So thanks to these additional channels, so they are not totally unimportant, they are actually quite important. They facilitate this laser cooling mechanism. Yeah?
But green light don't also have this another path.
This one has actually a very weak, yes, it does have, but that is extremely weak. This path, the ratio is not, for the n equal to plus minus 1, the ratio is not negligible. But for the green, this ratio is like, I don't know, like 10,000 to 1 or something. Is negligible. Okay? So this means you can do two things. Initialization. N equal to 0, 50%, n equal to plus minus 1, 50%. So this is thermal distribution. Can go to n equal to 0, 100%. That's called initialization, right? The other thing is detection. Okay, how is that? How does that work? So after initialization, you certainly want to do some quantum control. You want to manipulate the quantum states, right? So for us, the quantum states are these two. Okay. Actually, there are two pairs. Anyway, that's just details. But let's just say the n equal to minus 1 and n equal to 0. So say you, after initialization, you apply a microwave pulse at a certain pulse duration and pulse amplitude. And the result of that is that you pump about 98% of your NV. Maybe you miss 2% because of this and that reason, but you pump the majority of your members in your MV ensemble to the MV n equal to minus 1 state. Okay? Now, after this act, so initialization. So in our apparatus, we have two lines of electromagnetic wave. The first line is laser. The second line is microwave. usually we'll pump it for a while, long enough to make sure that all the cycles, we reach a significant amount of cycles, so that all the MV centers are prepared here. And then after that, we typically followed with a microwave pulse. So we turn off the laser, okay, and we just deaden state at the ground state, and then we turn on the microwave, and we do the excitation, and we want to see how many of them, the percentage ensemble average, how many of them are in the excited state. Yeah, how do we tell? So at this point, okay, so there are 3 points. At this point, you have n equals 0, n equal to plus minus 1, 50, 50%. Yeah. At this point, you have n equal to 0, 100%. N equal to plus minus 1, 0%, ideally. And at this point, so say you invert it, you make n equal to 0 obsolete, and n equal to plus minus 1, 100%. Yeah? Okay. So there are 3 points. Yeah? 3 time points. Now, how do you tell that this is the case? How do you tell that you have successfully get everyone to the excited state? That's what we talk. That's what we want to talk about here. If if you have the majority of your MV centers in your ensemble in n to the 0 state, then your fluorescence will be the strongest. Agree?
Yes.
Yeah, because here the radiative pathway is not the only way of decay. So if you have population here, then it's like you invest $100 and your return is, right? So for here, your return is $100, but here your return is like $80. So if you have population here, your fluorescence will certainly be dimmer. Yeah, your fluorescence will be dimmer. So what we do here is that we will shine another light to it, and we will detect its fluorescence signal. And we will take that fluorescence signal and compare with the case when there's no microwave. Okay? So in other words, we will run this twice. We'll do the experiment twice. One is without any microwave, that's the baseline. And one is with the microwave. Okay? So that's the experiment. And we'll compare these two. And the difference will tell us how much we have, how much difference we have in the ground state. Okay, so detection, so the difference, so m equal to 0 is brighter than m equal to plus minus 1. Okay, so this is the baseline, and this is the experiment. This is after the microwave excitation. Okay, by comparing the difference, we know the population difference. Okay.
When you use the microwave, you have our state from m equal to 1 to 0, and back just repeat this process in many times.
Yeah.
It happen if our microwave pulse is weak.
Oh, if my microwave is long.
Yeah.
So what will happen if my microwave is long? Oh yeah, you will oscillate back and forth. That's called Rabi oscillation. Okay, we'll talk about that later. Okay, all right, cool. So that's pretty much all I want to cover in today's lecture. So that's today we have overtime, but I hope that this is gonna be very helpful for you when you do the experiment. Now, of course, this is not completely. So what I cover here is the basics, is the foundation of this MV center quantum business. Okay, so this is the theory behind it, but the actual connection, like how does it disconnect to your experiment? That is the part that you need to do. Okay, I'm leaving that to you. You need to make the connection by either studying the menu, the Quantic menu, or the optics menu, or discuss with TA. Okay, or you can come and discuss with me during the lab session. Okay, but I'm leaving that to you because otherwise you will have no fun. You'll be told of anything, and then you'll be just like monkey cranking bars and taking data. Okay, so you need to think, how does what we teach here connect to your to the experiment that you do? Okay. All right. So as promised, we have peer instruction session questions. Let's take a 5-minute break, and then when we come back, we'll do the peer peer instruction quiz bonus, and yeah.
Can I make a suggestion on the time schedule?
Mhm.
Is that possible to get the class 1 hour before, like from 1:30?
Mhm.
If everyone is free, so we have some more time if you understand that.
Well, first of all, the previous class stopped at 2:10.
Here.
No, I mean for other people. So you're not taking the class before.
Okay, I'm asking whether all of them are comfortable with that.
Okay.
Oh, yeah, I see your question. If everyone
Yeah,
doesn't have everything before.
yeah, so we can extend, so like, even if you stay a bit later in the lab, it will not be too dark or something.
Dark.
No, it's already 6:30. It's like
Oh,
it will be like
yeah.
until 5:30.
About that. So the scheduled lab session goes to 6:30, right? Or 6:20. So you are free to go at 6:30. Okay, but the TA, I'm asking the TA to stay until 7:30 if there are people in the lab. So he'll be there to help you. If you want to stay longer and do the experiment, he'll be there to help you. You cannot stay past, I think it's 8:30. So I would prefer that you do not stay past 8:30. Okay, if you need more time to do the experiment, you can come another day. Just ask the TA for lab access, that's fine. Okay? Yeah, so if you want more time to do your experiment, you can stay a little longer.
And you also available at that time, everyone doesn't have class, then
Yeah, I'm sorry, I'm not available.
Okay. Yeah, then it's all right. It's
Yeah.
just a suggestion.
Yeah, but like I said, there are, if you feel like there's not enough time, but like I said in the first class, I have prepared your experimental session also enough that you should be able to collect all the data you need within the time I gave you. So even a little overtime, like 7, should be completely sufficient. 1 hour, 1.5 hours. If you know how the system works, then collecting the data is like super fast. Okay. Yeah.
Yeah, it's a question. So, for this wavelength, is this just some coincident to the laser's wavelength?
Yeah, we choose the laser according to this.
Oh.
So this is experimental measurement. This is not a theoretical calculation. This is they measure the peak
So
to be
we
this
make
value.
the laser for this wavelength.
Yes, yes.
But I think the wavelength, the laser is very common. This wavelength is very common.
Yeah.
For laser.
Yeah, yeah. So it's very convenient for us. It's cheap and convenient.
Yes. So
If it is 400, then it's less convenient. If it is 300, then that's almost impossible. It just happened for this system that it is at a very
Yeah, so-
friendly
Oh, I see.
friendly wavelength, and that's why MV Center is so promising and popular
Yes, you know what?
The other
because everybody can do it, even in the teaching lab.
Yeah.
All right. So let's get this done quickly.
I have a quick question.
Yeah.
It's okay.
Yeah.
I just want to make sure I understand correctly that the excitation from those states up here is done by the laser.
Yes.
Right. Okay. And this microwave, is this an excitation between these two states?
Right. Yes. Correct.
Alright, okay. And then we do
Because this is a small energy gap, and that's the microwave energy.
yeah.
That corresponds to that microwave energy. The laser energy is much larger because the frequency is higher.
All right. Okay. And then I have a question about this. So when we do the microwave pulse here, we excite it up to this state, and then we do like baseline and then measure it upwards.
But actually, we run this twice. The first time you do this.
Yeah.
The second time you do this.
We mean first time without microwave and second time with
Yeah.
microwave.
What's the difference?
So one, this is the first time. This is the second time. The laser is the same.
Okay, so the first time we don't have any microwave.
Right.
Oh, okay, I understand. But don't we have to do multiple runs with laser to get all of the states into the
Initialize.
to cool it?
I think
Correct.
this is the cooling, right?
Yes. Yes, you're right.
It just has to be long enough.
Long enough.
Okay.
Long enough. You don't need to do multiple rounds.
So the width of this is
That's for you to find out in the first lab.
Okay. So the longer it will be cooler.
Yes.
Okay.
Yeah.
Okay, then I get the graph.
Okay. Cool. Cool. Good. Okay. Let's go to the quiz questions. Everybody everybody excited about. Right. So, Lin, have you had a chance to review our lecture or our syllabus explanation last week? Yes. No. Have you watched the video?
Oh, I didn't watch it.
Oh, you didn't watch the video. So you probably will not know that we have many ways to earn bonus points in this course. Do you?
I don't know.
You don't know, okay. Well, then just go along, okay? Just go along. In the absence of an external magnetic. Someone please help me close the doors. Thank you. How many qubit pairs are there in the ground state triplet? Okay. Okay, last time I say I'm gonna give you two options, right? I feel like there's not much fun if we only have two, so I'm gonna do three. I'm trying to do three for all quiz questions, so it's the process is more fun. Okay. All right. So I want everybody to come up to the front and stand in the line behind the answer you think is most probable to this question. If you don't understand the question, you can ask. but I'll only provide very limited information.
qubit pairs. What is qubit pairs?
Because qubit takes how many states?
3 above.
A qubit takes how many states?
Oh, okay.
All right. So please stand up and then we need to save time, right? Otherwise, we don't have time for experiment. So let's try to be more efficient. Pick your answer. Pick your answer. I must warn you, this is a trick question. Okay, this is a trick question. All right, I'm gonna count down 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, nobody moves. Are you 0? Okay, are you 0? Okay, all right. You two, come to the front. You are 1, right? And you're 2. Okay, so I want to make sure everybody have an answer. All right, now I want, so like I said, okay, you need to listen. Like I said, we need to try to grab somebody from a different line, preferably not from your own group, and convince that person that your answer is right, and try to get him to your side. Okay? So you will.
Small question.
Yes.
Is a superposition state seen as one state or two states?
Superposition. Superposition is one state because it's a 2 electron state. It's 1 2 electron state. Okay, you stand here, and you will go over there. You will talk with Phoenix, and you'll talk with Masfa, and then, well, we have a odd number. So, are you sure? Well, without even convincing, okay. Why don't you talk with her, and then you, yeah, you 3, okay? I'll give you two minutes to discuss. We will have at most 2 rounds of discussion, and then we will get our final answers. Right? Whoever gets both questions correctly will get a quiz bonus point of 1. All right.
My thinking is like we have like the when you go to zero state is like the superposition state, and we have the individual state m equal to. So I think next time when you go to the when you go to 0 state.
Actually, the concentrate means
They are separate in
Next time
can we use a
Yeah.
whiteboard?
Yeah. Yes.
So this is
Alright, to make sure I'm
so this is the concentration, and
depending on the
so
so
so what's the meaning of
no down state triplet means there is like 2 more states. One is this state, and another is this state.
okay?
So I think in the absence of examples, these 2 states will not be there. Only this state will be there.
What's the meaning of
are aligned, right?
Qubit pair is this pair. This is 1 pair. This is 1 pair. This is 1 pair. That's
or you mean or this is the qubit?
so that's why I asked him whether this is 1 pair or 2 pair.
How many? Also,
Ground state, when it's not the excited state, basically.
Means I mean there is some
So, but it's
magnetic
both
field
the
should be
M has
there
0
for this
and the
space.
M has 1.
Oh, the minimal is
zero.
this one, so at maximum point this will go to this state. So only
Yeah,
one
but
state.
don't,
As far as
Q,
that's the concept I get.
I mean, it can be one pair in each.
Also, you mean this one is the box.
These three are ground states.
But this,
No, that we got, right?
the fine structure, this one is the box.
Yes.
No.
Yeah. Exactly.
Yeah.
We have up and down,
Oh,
up and down,
so you
up and down,
and this
down, down.
small state is only one. Cubic.
Yes, one.
That,
Um,
or then that.
but maybe this is not what we're talking about.
This is a certain structure. I think that what he mentioned is like if you have one state, that state can be split into
Yeah.
or zero. And then we have 1, 2, 3 states.
30 minutes, 30 seconds.
0, 1, 2.
Oh yeah, but the question is how many cubic meters?
But okay, yeah, what's your everything lies in what he mean with cubic pairs.
So the cubic pairs is like cubic pairs multi-pair.
So this is not really
Hmm?
cubic pairs.
Richard is meant multi-pair.
Two state is a pair.
One, two state is a pair.
Yeah, a pair means two, right?
Two state. Is ms equal to 1 or minus 1?
It needs two
Different
cubic,
states or
two cubic.
same state.
What do you think?
Cubic means it's a level system.
Yeah.
Go up and down. One.
Oh.
Pair means there is two atoms. That's two people.
Ask people, do you think n equal to plus one, minus 1 is same or different? All right, time's up.
That's why I'm saying the one.
All right, stop, please. All right, now stand back, get back to your line, please. Now you have the chance to switch your position if you want. Okay? Do it now. Nobody want to change?
Yeah, I changed. But I still can't.
Okay. All right. So now we have 5 in this line and 4 there. All right. Now you guys need to convince them that you are right. Okay? So and you do the same. Try to argue with them. So I'm gonna get you 2 and you 2 and you 2 and you will do this too. Okay? Try to convince each other that you have the right answer.
There are three cubic pairs.
This is a pair of pairs.
Maximum
But it's not the definition of cubic
So,
pair. You think so?
in the absence of
Well,
external
what I think
division,
is
no external division.
we have
So I
a
think you go to the max
Yeah,
state.
like,
There is no, it's like the most.
This is why is the box
Actually,
actually because
But
consider
you
the
cannot
whole
do
structure.
three
will not have.
usually either get
So only
like
one will be there. One cubic pair.
the whole is all 0 or plus half, one or
So this one is a compression.
one.
Yes.
If I understand the question correctly, I would say it's wrong.
Don't think so because the energies come from like
This whole thing is a pair.
magnetic
Yes.
dipole.
An electron
So
is a cubic meter.
These two, so in your mind, electron state is a cubic.
So this
But in my
two will
mind,
give you positive
I'm still not sure about the definition of a cubic pair. That's the problem for me. But I understand what this one is together. But I'm trying to think in terms of electrons. Maybe I cannot do that.
So what a cubic is
Like because you said, because in this case, spin is 1, right? So I
equivalent system.
On average, down,
So
right?
from here you go up and down. That's another two level system.
Yeah.
We have 1 minute left.
But I don't know.
That's another two level system.
I would say here we have one
So
cube
this is
state,
one
easy
cubic
drum
pad.
station. Here we can have two cubes.
It is not like
These two are degenerated, yes.
Yes.
No, this is not the two level system. Two level
What's
means
the
you
distinction
go
of a cubic
exactly
pair?
come down.
What's the difference?
That's the two level system.
This is a pair,
This is not
and it would be,
This
no,
is
with three plus
Also,
eight,
each
this
three
is
different
three plus
each
eight, right?
straight.
Isn't this one pair and then two pair, but then you say we degenerate, so you say it's one.
Oh, I see. Yeah, then, so this is just.
No, this is not group discussion. You need to discuss with your partner. You have a partner.
Yeah.
Stay with your partner.
Okay, I see your point, I see your point.
Yeah, I think the fine structure is.
Okay.
This is one pair.
20 seconds.
This is one pair, this is one pair, but they are degenerate, so you always.
20 seconds.
Yeah,
So
because
do we need external
we can
magnetic
take your
field?
point.
Yeah, we normally have some magnetic field or something
But I was
in our
confused
lab,
because
right?
first I was
That's why
thinking
we
this
have
as a
three
pair, but
states.
this is
That's
just
what I
lower
believe.
end.
So to get a fine structure, we need external
It's
magnetic
like
field.
A1 and A1
Really?
prime and stuff.
Because there
That's
is
not
a
related to
vibration,
this question, I
that's
think.
some
That
field, right?
influences.
Already.
Oh yeah, so maybe I can check.
Okay, let's get back to your line, your original line. Thank you. We have 5 here, 4 there. All right. Anybody wish to switch lines? Do it now, please. Okay, we have more people in line 1. Anyone? Convinced? Not convinced? Okay. Do we need another round of discussion?
Yes.
Yes. Do you think we need another round of discussion? Another 2 minutes? All right. Okay, I'll give you another round, okay? So this is extra. All right, just pick someone randomly and then start discussion. Preferably somebody I have not talked before to get a third opinion.
I'm not sure.
And stay with English, please.
We had due to electric field half spin.
No, but if
Grab someone. Everyone must have a conversation discussion partner.
then the ground state should be the same.
Microsoft plus all.
Which one?
Like cubic states, I think it's we are in the triple state, right? We are in this
The reason why the bottom one is positive because we have fine structure. But you say
Even though it's not there, there is at least
Yes.
One
integrity.
here.
The atom should be arranged.
One somewhere there up here.
This is not, is this
There will
triplet
be
or
fine
something?
structure because of the molecule, but there won't be exact.
Isn't it singlet when they are in the same direction? Or what's the singlet one?
I think we don't need any magnetic field because just have some space with carbons.
But still, it will not be populated in.
Now
Oh, we are doing
So,
like
so
this.
I say so because there is a condition called in the external so I think
Do you have anything?
It should be one up and one down. Otherwise, it would be some zero, right?
The molecules are there.
I think it's just the splitting carbon because in this case and the energy.
but so
Send direction will be a minus one.
It's very, very
So that's why this one is have a lower energy. And even without
1 minute.
Yes,
So
but
this one is
this,
a false.
if you do
so the ground state triple is
this, then it's M equals zero, right?
in the example.
Yes.
If this
It's only
situation
one-
one up
one-
and one
Yeah,
down,
so this is only one.
then you get M
That's what I-
equal
Yeah.
zero,
Oh,
yeah.
okay.
But isn't that a
Because you
singlet
told
state?
me that to get this fine structure we need external.
this is
That's I'm wrong, I think. Yeah.
Oh yeah, I just not sure for this notation. I don't know. Did he? I think he mentioned this during the class.
All right. Okay. Get back to your line, please. All right. All right, guys. Get back to your line. Get back to your original line. Original line. Thank you. And now we have 3. All right. If you wish to switch lines, do it now, please. You're the brave one. I like you. So you're 2, right? You stick with 2. Good. You're the brave one. All right, cool. You see how the distribution evolved? It become peaked, like Bose-Einstein. Compton said, it become peaked. All right. Well, the answer is 0. Okay. All right. For the sake of time, we won't go into more discussion here, but that's something to think about. All right. So the second question is, how many free electron, does MV center have? Does MV center have? So Sam, MV minus, the one we use. 4, 6, 8. All right. Take a line, please. Wow. The distribution is very sharp. Okay. But we're still gonna do at least one round of discussion, even though everybody picked the same answer, maybe for different reasons. So we're still gonna have people. So I guess you 3 will talk, and you 2, and you 2, and you 2. All right.
Now we try to count them together, right? So we have a vacancy here, a nitrogen here. Yeah, we can do it over. Like we have vacancy, nitrogen.
Where does that come from?
This has
Okay, so
there is a
Oh yeah,
we get one
So
electron
this
from
has
this
like
part,
5
right?
external electrons.
Yeah.
And the 2 are like
No, this doesn't have
Still
that.
here.
He wants to mention this one.
Yeah, because due to the being negative
you like
charge, you have
yeah.
to have this one.
And then you get one from another one, yeah.
Oh, sorry. Yeah,
Zoom.
I think the
Yeah, right,
reason why
because
is
these are not really
the
what
first
this
question
is
is
bounding with.
the cubic parents for the first question is 0
Because
because
back when you did like this,
there
this
is only
the-
one
these
ground
are
state.
paired up in the
The ground state triplet, there's only one
Basically,
ground
one,
state triplet.
two, three,
So
four,
there is
five,
no cube. Because if we want,
six.
then we have to have a
the
2 levels
have is and we state is
like
this.
2 say.
1,
You have
2,
to
3, 4,
create
5.
Yeah, I think that's right.
This is the state we have.
Because we needed that final one to make it out.
Yeah.
Okay, this one here.
No, I just trying to understand what the
This is
question
vacancy,
is.
so there is no bond.
Yeah, because this has 5 electrons.
Because
And
if
there's
we
2 in the inertia and 3.
20 seconds.
No 2 levels.
And this 1, 2, 3
There is
findings.
no 2 levels.
This has no
then
3
there is no
electron.
And
These
copper, right?
electrons are
Then
yeah,
It's your
available
Now,
from
because for the
the
ground state,
vacancy
then
and
there's
then have
only one
the
level.
last one.
Holy.
And because it's called ground
Sorry,
state,
it's so hard for
only
me to
ground
pronounce
state is
this.
the lowest energy state.
IKEA.
No, it means the ground
IKEA.
state. So
No,
there's
that's
only
English.
one
Thank you. IKEA.
All right.
It's good if I feel homesick, I go to IKEA and I feel like I'm
No, so,
homesick.
All right, stop.
So I think only this one.
Okay.
Yeah, so this, so
Stop your discussion.
yeah, so this
Get back to your line, please. All right, if you wish to switch line, please do it now. Nobody want to switch? Are you sure?
Yes.
Are you positive?
Yeah.
All right, so I guess we don't need another round of discussion. All right, congratulations, everyone got this correctly. It is 6. All right. Okay. Now, so is this fun? I think so.
Have you heard about board game? Like if you're like, since no one got right on the first one, then I think you should get -1 bonus point because when it's too hard a question. It's -1 bonus point for you.
Okay.
Actually, one should get-
I will say that the key word for this is qubit, and qubit must be closed system. That's something you want to consider. That's the primary criteria, closed system. When you think about this, that's the keyword, closed. Okay? All right. So for the sake of time, let's move to the lab, rush to the lab and start doing your experiment. Now, the TA is there. And I will, so Ling, I will give you a quick introduction on optics for safety. Not here in the lab. So